Greetings everybody. So in the previous video we took a look at multiple choice for Specialist Maths Exam 2 and now we're going to continue on with where we left off with some short answer questions. Alright, so section B, question 1. We want to sketch this graph on the axes below. So a good thing to do is maybe let's start a new problem page. So we're going to do doc for 1 and I'm just going to define this function f of x to be equal to, we have 3x over x cubed, and then we have a plus x plus 2. Alright, dot 4 to graph f of x. So it seems like we have an inflection point and a turning point here with an asymptote, horizontal and vertical. So what we can do is we can define df of x to be equal to the derivative is x, f of x, and define ddf of x to be equal to the derivative x and then df of x, and we can solve df of x equals 0 with respect to x and solve ddf of x equals 0 with respect to x. So we get x equals 1, so f of x at x equals 1 is 3/4. F of x at this inflection point is 0.59. Alright, so we get 1, 3/4, so we get a point somewhere over here, that's the turning point, and so let's label this, so this is 1 3/4, and then the inflection point is that's going to be 1.7, so somewhere over here, and then 0.6 roughly, so it's going to be roughly here. That's going to be the inflection point at 1.7, 0.6. Okay, let's find the asymptote, so we'll do domain f of x, x. X is not -1, so there's our asymptote over here. And because the degree of the denominator is greater than the degree of the numerator, we get an asymptote at y equals 0 as well. There's no constant term. Alright, so if we try to plot this now, let's take a look at our graph again for reference. We have something, so this passes through 0, let's just check that. F of 0 is indeed 0, so we pass through 0 and we get some kinds of turning points here and then inflection points, so something like that. We should label as well y equals 0, x is -1, and then the other branch looks something like this. Alright, so that's our graph for 3 marks. Let's just check. We have asymptotes, we have turning points and inflection points, and 1 decimal place. Alright, region bound by the graph of this thing, the coordinate axes and the line x equals 2. So x equals 2 is over here, so we're after this region here. This is rotated about the x-axis, write down a definite integral, so that's just pi, integral from 0 to 2 of 3x over x cubed plus x plus 2. This is all squared dx. Let's plug that into the cos because we want to find the volume. So we're going to do pi times the integral from 0 up to 2 of f of x but squared dx. Approximates, that's 2 points, this is up to 2 decimal places, so this is 2.29. Find the equations of the vertical asymptotes of this guy. So we'll do domain, we have 3x over x cubed minus 5x plus 2, comma x. So let's write that down. We have x equals, that's going to be -√2 minus 1, x equals √2 minus 1, and x equal to 2. So those are the vertical asymptotes. Part D, a family of curves is given by y of x is equal to this. So let's maybe define a new function, say g of x equals, we'll do 3x over x cubed plus a times x plus 2. Consider the case where the graph has a stationary point P. Find the coordinates, y coordinate of P in terms of A. So we'll define dg of x equals the derivative of g of x, and we'll do solve dg of x equals 0 with respect to x. And we're going to plug x equals 1 into g. So g of 1, that's going to be 3 over a plus 3. Okay, so y coordinate is just 3 over a plus 3. Maybe if you really want to, you can write down some working out, but this is just 1 mark. For a given value of a, the graph has no stationary points. So that's when a is equal to -3. Find the equations of the vertical asymptotes. So we'll just do domain of g of x, comma x, when a is -3, and we get x equals -2, and x equals 1. For a given value of a, the graph will have a point of inflection at x equals 2. Find the value of a. So point of inflection, let's maybe define ddg of x to be the derivative of dg of x, and then we want, what do we want? We want to solve dg of, we want this inflection point to be at 2 equals 0 with respect to a, and we got 24 and 5. So if we just if we just take a look at y double prime of 2 to be equal to 0, then this tells us that a is equal to 24 and 5. It's 2 marks, maybe that's enough working out, I don't know, but yeah. Alright. Question 2. So we have some complex subsets here. We want to first of all sketch z bar equals 4. So recall that z times z bar equals mod z squared. So we're sketching mod z squared equals 4 or mod z equals 2. So that's just going to be the circle of radius 2 centered at the origin. Something that looks like that. Okay. We'll show that this is going to end up being a line here. This may be expressed as y equals √3x. So what we can do is we can take a look at the squares, and we can just let z be equal to x plus I times y. So if you do that, you're going to get modulus of, this is going to be, well, z is x plus iy, so we just get an x, plus iy minus 2i, but you can factor out an I, leaving you with y minus 2 squared, and this is equal to, same thing here, we have, this is going to be x minus √3 now squared, plus an I, and then we have, that seems like a y minus 1 squared. Okay, so if you expand everything out here, sorry, there shouldn't be a squared here, the squared should go on the outside. And then when we take the square, that's when we, put the squares here. So x squared plus y minus 2 squared, and this is equal to x minus √3 squared plus y minus 1 squared. So remember, if you take the absolute value of z squared, if z is equal to a plus bi, let's say, then this is just equal to a squared plus b squared. That's Pythag. Okay, so we can expand some things out here. So this is x squared plus y squared minus 4y plus 4, and this is equal to x squared minus 2√3 times x plus 3, and then we have a y squared minus 2y plus 1. Some things cancel, x squared and x squared, y squared and y squared. We have this 4, this 3, this 1, leaving us with, let's see, we have a minus 4y and a negative 2y on the other side, so that's going to be negative 2y equals negative 2√3x, or y is equal to √3x. Okay, we want to sketch this line, so that's going to be, well, √3, that's a gradient of √3, which is an angle of pi on 3. So our line is going to look something like this. So this is the angle pi on 3. Okay, and we want to find the point of intersection of the curves defined in part A and BI. So those are these points over here. And, well, the points are just going to be, it seems like a plus or minus 2 cis pi on 3. So that's going to be plus or minus 2. We have, what's cis of pi on 3? That's something like a half, and then plus I times root 3 on 2. So that's going to be plus or minus. We have 1 plus I times root 3. So let's label those points. We want to find the points of intersection. So yeah, that's going to be 1 plus I times root 3, or minus 1 minus I root 3. So let's plot those points. That's 1 plus I times root 3, or minus 1 minus I root 3. That should be it there. Okay, so we have labeled these points. Okay, perfect. And then the next question, consider the points P and Q. A ray originating at point P passing through Q has the equation argz minus z naught equals theta. So this is what the line looks like here. Write down the values of z naught. So z naught is going to be, well, z naught is this coordinate here in complex form. So that's going to be 3 halves and then plus I times 3 on 2. And theta is going to be the angle this makes with the positive real direction. So the principal argument is between negative pi and pi, so theta has to be negative pi on something. So how do we compute that? Well, we know this is an equilateral triangle here, because, well, this angle is already, we know that's equal to 60 degrees. So the other two angles are also 60 degrees. So let's see here, if this is 60 degrees, then this angle here should also be 60 degrees because, well, this line over here is parallel to the real axis, and this angle here and this angle here are the same. There's probably a better way of explaining this, but yeah. So we have a 60-degree angle over here. So yeah, pi is equal to negative pi on 3 as well. Okay, find the area of the minor segment bounded by the chord connecting the points PQ. So the minor segment is just going to be this part over here, and the circle given by, okay, so we just want to find the area. So the area is given by the area of this whole sector, which is, so let's say sector area. That's going to be, how do you do that? It's equal to, what's it? The angle times the radius or something like that. I'm forgetting the formula. So let's derive it from scratch. It's equal to the angle divided by 2 pi times the area of the circle, which is 2 pi times r. Sorry, that's not right. That's pi r squared. So if theta divided the angle, it's the angle divided by 2 pi times the area pi squared. Okay, that should be fine. And if we simplify this, this is theta times r squared over 2. Okay, so the sector area, r is equal to 3 in this case. So this is equal to pi on 3 times r squared, that's going to be 9, and then divided by 2. So that's going to give us 3 pi divided by 2. Okay, and then we also have this area of the triangle. Let's shade that in yellow. So what's the yellow area? So this is a triangle area. The triangle area is this going to be, well, the area formula, if I remember right, it was something like a half times AB. Was it sine theta? I think it was sine theta. Half. It was half, so in this case it would be 3 times 3 times the sine of pi on 3. So this works out to be 9 on 2. Sine of pi on 3 is root 3 on 2. So this gives us 9 root 3 divided by 4. So the area, let's see, minor segments area is equal to, we take the sector area, which is 3 pi on 2, and then subtract of 9 root 3 on 4. We want to express it in the form c pi plus d, which we have. Okay, so hopefully my hands computations there were right. I could have used it as a cas, but it is what it is. All right, question 3. We have a mixture problem with differential equations. A tank initially contains 5 kilos of salts dissolved in 3,000 liters of water. Okay, so we have the inflow rate is 20 liters, the outflow rate is 20 liters, and by considering the concentration, explain whether the quantity of salt in the tank increases with time. Okay, so what is the concentration? The concentration, the initial concentration, let's say, so initial concentration is, that's going to be 5 over 3,000. And what is 5 divided by 3,000? 5 divided by 3,000 is, let's do, approximately equal to 0.001, 67 or something. Okay, but what's the concentration of salts coming in? So that's the initial concentration, then we have the inflow concentration. The inflow concentration is exactly 0.1, and because 0.1 is greater than 0.00167, the concentration will increase. So yeah, salt increases. Okay, so now we let Q be the salt in the tank, and we want to show that Q satisfies this differential equation. So let's see, dQ dt, this is equal to, well, we can take a look at the inflow rates of salts minus the outflow rates of salts. So what's the inflow rate? The inflow rate is precisely, well, we have 0.1 liters, so 0.1 kilograms per liter times 20 liters per minute. The outflow rate is precisely, well, however much salt we have in the tank divided by the volume of the tank, which is 3,000. So this is the concentration here that's currently in the tank, and then we multiply this by the outflow rate, which is 20. Okay, so this simplifies to 20 minus Q over, and then we have, that's going to be 150 down there. That's not going to be 20, that's going to be 2. And well, this gives us 300 minus Q over 150. Using Euler's method with a step size of 15, finds a Q of 30, the approximate quantity of salts. Okay, so let's recall the formula for Euler's method. It's yn plus 1, or I should write qn plus 1. This is equal to qn, q1 cubed is 3, and then plus, in this case, h is 15, times q prime of, let's say, tn. Okay, so first of all, so this is the formula we use. So let's calculate the formula, the value q1 first. So q1 is equal to q0. So what's the initial amount of salts? It's exactly 5 kilograms of salts. So this is 5, and then we have a plus, that's going to be 15 times q prime at 0. So at 0, q is equal to, well, is it 15? No, it's 5. Right, so it's 300 minus 5 over 150. So let's compute that. So we have 5, and then we have plus 15 times 300 minus 5, and then divided by 150. And this is giving us 69.2 or 34.5. And then we have Q2. This is equal to Q1, which we just computed to be 34.5 plus 15 times 300 minus, that's going to be Q1 once again, so 34.5 now divided by 150. And this is giving us, let's do the computation again, so 34.5 plus 15 times 300 minus 34.5 divided by 150. And this is giving us 61.05. Okay, let's verify this with the Euler's method command. So this is Euler. We plug in the differential equation, which is 300 minus q over 150. We have the independent variable, the variable, and then the parameters for the independent, which goes from 0 up to, and we want 30 in this case. We want the initial value for the dependent, so that's going to be exactly 5. And then we have the step size, which is 15. So let's check back 61.05. Perfect. All right. Part D, we have use calculus to solve this differential equation. So this shouldn't be too bad to do. It's just separation of variables. So we have 150. Well, let's actually bring 300 minus q to the other side. dq over 300 minus q equals dt over 150. So integrating both sides gives us log 300 minus q, and this is equal to 1 over 50 plus c. So let's see now. This is t, my bad, and we know q of 0 equals 5. So plugging that in, or we can plug it in later. So let's see if I can remember how to solve this. So we have 300 minus q, and this is equal to, that's going to end up being some constant a, e to the t on 150. And we can get rid of these absolute values and dissolve it into that constant a there. And we have q, that's going to end up being 300, and then minus a e to the t on 150. Plugging in t equals 0, what do we get? So t equals 0. We want the q to be 5. So we want 5 equals 300 minus a. So it seems like a is 295. So therefore, we have a q, and this is equal to, well, that's going to be 295 e to the t on 150. Let's verify that. Oh, plus, this is minus and then plus 300. Let's verify that on the CAS. So we do d solve, and we plug in q prime equals 300 minus q divided by 150, and q of 0 equals 5 tq, and seems like we're missing something. So why is there a negative? Oh, because when I chain row, I forgot a negative here. Silly me. So negative there, and this ends up being, well, really we're missing an extra line. There should be. We bring the negative to the other side here. All right. I'm forgetting how to do calculus. All right, part E. What value does the quantity of salt in the tank approaches as time approaches infinity? Well, as t goes to infinity, well, I'm missing negatives here. Negative, negative. This exponential term vanishes, so it's just going to be 300. Find the time taken for the quantity of salts to reach 100. So what we can do is we can just solve 100 equals, let's grab this, and then solve this with respect to t. Approximates this is 58.29 minutes. It doesn't say how accurate, so let's just say 58.29, or let's just say 58.3 minutes. Does it say how many decimal places it wants? Maybe not, we'll just keep it as that. When the quantity of salt in the tank reaches 100 kilograms, the tap draining the tank is turned off. Assume that the tank does not overflow. So the volume is always going to be equal to, it was 3,000, wasn't it? 3,000. And now we're no longer going to have outflow. So right when the tank reaches 100 kilograms of salt, we have Q equals 100, right, and V equals 3,000. And now we're only going to have inflow. So the concentration is going to be Q of T. So really these are the initial volumes and the salts now. So Q of T, sorry, my bad. Let's say, yeah, the concentration with respects to T is just going to be Q of T over V of T. Q of T in this case, because the outflow turns off, Q of T is just going to be, we have 100 initially, and then plus however much we're adding on each minute. And that's going to be, well, we have 20 liters coming in per minute of water, and each liter contains 0.1 kilograms of salts. So that's going to be 0.1 times 20 times T divided by 3000, which is the volume, and then we're adding 20 liters each minute. And then we're just going to set this equal to, what do we want? 1 on 20. Let's solve that on the CAS. Nice and simple. 1 over 20 equals, that's going to be 100 plus 0.1 times 20 times T divided by 3000 plus 20 times T. Solve with respects to T, and seems like we just get 50. T equals 50. We'll go with that as the answer. Alright, so let's take a look at question 4. So we have a path of a moving particle with this position vector. And what do we want to do? We want to write down the coordinates of the particle's starting points. So let me first of all define this path r of t, and I'll open up a new problem page to do this. So we're going to define r of t to be equal to, we have 5 times the cosine of t minus 4 cosine of 5t on 2, comma, 5 times the sine of t, and minus 4 times the sine of 5t on 2. Okay, and we're going to take a look at r of 0. So this is just 1, 0. Nice and simple. They're really giving us quite simple and short questions in this exam. For part B, on the graph above, draw an arrow from the point 9, 0 to indicate the direction of motion of the particle. So, well, what we need is probably dr of t, the derivative. So we'll define dr to be just the derivative with respect to t of r of t. And, well, I don't know what time the particle will go through 9, 0, but we do know the initial point, which is 1, 0. So why not plug in dr of 0? I didn't even define that, silly me, to find dr of t to be equal to this thing. Then we can take a look at dr of 0. That's 0 and negative 5. So this is telling me at 1, 0, this position right over here, our particle is traveling in this direction. And if we just trace this around, we should find that at 9, 0, the particle is actually going upwards. So let me just draw an arrow right over here. We probably shouldn't have all these other arrows here. Find the value of t for which the particle will return to its starting point. Well, what we can do is we can just solve r of t equals to 0, 0 and see what we get. Starting point is not 0, 0, it's 1, 0. So it looks like we get t equals 12.5664. We can verify this by what we can do. Let's plot this. Let's do 4, 4, and then what I'm going to do is I'm just going to plot, say, the x components of this function. So I'm going to Control C that, Control V, replace all these t's with x's, and let's see. Yeah, so we get a nice repeat over here. So we start at this local minimum, we do all this crazy stuff, and then we end up, this is one period right over here. And this seems to be around, 12.5 roughly. Was that what we got? 12.56, yeah. Okay. This is, how many decimal places? Or maybe it's it's probably a multiple of pi. And we can probably get that by taking the lowest common multiple of the periods here, which is, well, that's going to be 2 pi, and that's going to be 2 pi over 5 on 2, which is 4 pi and 5. So it seems like if we do, yeah, 2 pi, maybe like, is this 4 pi? What is 4 pi? Yeah, it's exactly 4 pi. So this is exactly 4 pi. Because, yeah, lowest common multiple, well, if you just take 2 and 4/5, then, well, lowest common multiple is just 2. Well, no, it's not 2, it's 4. LCM of this is 4. Does LCM work for fractions? I don't know. I'm just making up maths here. Show that the speed of the particle in meters per second can be expressed as this. So let us just take a look at the norm of dr of t. It's this thing which supposedly is equal to the square root. Can we see why it's equal to that square root? Let me just type in that square root. So square root of 125 minus 100 cosine 3t on 2. Oh, so it does simplify to exactly what we... Doesn't? Not quite. What if I do this and then minus this? Do I get 0? I don't. Is my dr of t wrong then? Let's try that again. It was square root of 125 minus 100 cosine of 3t on 2. And if I do this minus this, I'm not getting 0. So let me see if did I even copy down my r of t correctly? So it's 5 times cosine minus 4 cosine, and then 5 sine minus 4 sine. So maybe the Kazs can't simplify this. So, well, the first thing that comes to mind if I try to equate to these two is just the double angle formula. Not the double angle, the angle sum formula for cosine. Because you'll notice in this expression we get cosine cosine, and then we have sine sine. So this looks like double angle. So let's just take a look at this following expression. If we take a look at cosine of 3t on 2, well, this is just cosine of 5t on 2, which is what we have, and then minus t. Right, but by the double angle formula, the angle sum formula, this is cosine of 5t on 2 times the cosine of negative t. Well, actually, we can use the angle difference formula. So this is going to be cosine of t now. And then plus, because it's negative here, so for cosine, the sign changes. And then we have sine of 5t on 2 times the sine of t. And that seems to match what we have there. So if we just take a look at the norm of r prime of t on our Kaz, this is equal to, well, 5 square roots of negative 4 cosine of t, cosine of 5t on 2, and minus 4 sine of t, and then we have sine of 5t on 2, and then we have plus some extra stuff there, which is just a plus 5. Okay, well, this simplifies to 5 square root of minus 4, and then you'll see if we factor out negative 4, we get the cosine of 3t on 2 back, and then plus 5. Okay, and this gives us, if I just bring the 5 in, so multiply everything inside by 25, we get 125 minus 100 times the cosine of 3t on 2. Maybe what's left for us to do is actually show this equality, which hopefully shouldn't be too bad to do. You'll just have to expand out a bunch of stuff and maybe things cancel. Am I too lazy to do that? Probably. So yeah, maybe if we just call this, oh, does it simplify nicely? You would just get a bunch of squared, cosine squared, and a bunch of sine squared, and yeah, it should simplify quite nicely. I believe. Okay. There's probably more working to be done here, but I'm too lazy to expand things out. Okay, what is the maximum speed of the particle? Well, let's just maximize the inside of this square root here, and the maximum will be 125. The range of cosine is -1 to 1. If you select -1, you'll get a plus 100, so that's going to be 225. So taking the square root of 225 is 25. Is that the square root of 225? Hopefully. No, it's not. It's 15. I think, yeah, 25 squared is 625, not 225. Okay, on the page, on the graph on page 18, trace the path of the particle for t from 0 to pi. So what is r of pi? It's -5, -4. -5, -4 is right over here. That's nice. And, well, we said at the starting point we're going down. So from 0 to pi, we're going to get a path. So starting here at 1, 0, ending at -5, 4, we're going to traverse in this manner, it seems like. So something like that. Just as a sanity check, we said the period was 4 pi. And we're only traversing a quarter of a period here. So does this look like a quarter of a period? Kind of, because if this was a third of a period, then our points would reach to around over here. And a quarter is a bit less than a third, so this checks out. Okay. Find the length of the path traced. This is just integrating the speed. So we do shift plus from 0 to pi of dr, actually norm of dr of t with respect to t, and this is 36. Answer in meters, correct to 1 decimal place. So this is 36. I should do integral from 0 to pi of the norm of r. Actually, in special, you don't care about double lines, so r of t dt. Maybe that's enough working out, I don't know. 0.6. This is 1 decimal place, so just 0.6 will do. Okay. Yeah. So 36, does this make sense? So an arc length of 5 roughly looks like maybe, I don't know, this segment's over here. So can we fit roughly seven of them in? So 1, 2, 3, 4, 5, 6, 7. Maybe I drew those a bit too small, but it seems plausible. Right, maybe if I tried that again. So there's 5, there's 10, 15, 20, 25, 30, 35. Yeah, just as a silly sanity check, I guess. Seems correct. Yeah, I want that curve back. All right. All right, so let us take a look at question 5 now. So this is a vector equations question. And, well, we have these 3 planes and we want to find the point of intersection. So let me first insert a new problem page. And what I'm going to do is I'm going to define these 3 planes. So I'm going to define pi 1 to be equal to 2x plus, that's going to be 9z equals 8. So this is something you can do in the CADs. You can define variables to be an equation. So if I type in pi 1 now, it's taking on this whole entire equation as a value. I'm also going to define pi 2 to be equal to 3x plus 6y plus 5z equals 7. And I'm going to define pi 3 to be equal to x plus 9y minus 3z equals 7. And to find the point of intersection, it's very simple. We just solve pi 1 and pi 2 and pi 3. So literally just solving them simultaneously for x, y, and z, giving us -5, 2, 2. So we have -5, 2, and 2. Finds a vector that gives the direction of the line of intersection of the planes pi 2 and pi 3. So there's a few ways you can do this. What you can do is the same thing as we did before, but you just omit the pi 1 now. And it gives you this sort of sort of expression. So your direction vector now would just be the coefficients in front of these C1. So these C1s, these are just unknowns, or you can think about them as a time parameter if you want. So it would just be -3, 2, and 1. Because this is 2 marks, I should probably do some working out. The proper way to do this sort of question is to actually take a look at the normal vectors. So we have n2 and n3. N2 is equal to, that's 3, 6, 5, and n3 is just 1, 9, -3. And the direction vector would just be the cross product. So let us compute the cross product of n2. I haven't even defined it. Maybe I should define it actually. That might be a good idea for later. Define n2 equals 3, 6, 5. And I want to define n1 equals 1, 9, and -3. And I'm going to take a look at, sorry, not n1. What am I doing? n3. Let's del by n1. And let's take a look at the cross product of n2 and n3, giving us -63. We have 14 and we have a 21. Can we factor this at all? I think so. I think this factors out. If you divide everything through by 7, this is -9, 2, and 3. That seems right. And you'll notice this well, should match. It's a scalar multiple of the vector we saw in this equation. This is the reading -3, 2/3, and 1. If you multiply this vector we got from this expression by 3, you get whatever we just wrote down. Okay. Part 2, find a set of parametric equations that give the coordinates of the points that lie on this of intersection. So well, we need x equals something, y equals something, z equals something. And do we know a point that this passes through? Well, we have the point of intersection, so I guess we can just write x, y, z equals, we have -5, 2, and 2, and then plus, or maybe we should do negative plus plus. We have a 9, 2, and 3, and then we'll just tack on a t there. Yep. And t is in R. Okay. Question part C. Find the shortest distance from the point 1, 1, 2 to the plane pi 3. So what we can do is we have our plane here. Let's try to find a point on the plane. Let's call it P3. We have this other point. Let's just call this one P. And what we'll do is we'll find a vector from P3 up to P. And we'll just project this vector onto the normal vector, N3, and then we'll find the length of that projection to the scalar resolute. And that will give us the shortest distance. Maybe it's more illustrative if I draw the normal vector over here. That's our N3. And then we're finding the vector projection, which will give us this yellow vector here, and that's going to be the shortest length. Okay. There's also a formula for this as well, which I don't remember, and I don't have the formula in front of me, so I'm just going to do this from scratch. Okay, so first of all, let's find a vector P3. So what's a vector P on our plane? If we take a look at the equation of our plane, P3, if we just set 1, z equals 0, we get x equals 7. So a point we can choose is 7, 0, 0. This vector, let's call this vector, this red vector v now. So v is equal to, well, I'm going to take the difference. I should define, let's define P3 to be equal to 7, 0, 0. And I'm going to define P to be equal to the vector in question, so 1, 1, 2. And I'm going to define a v to be equal to the difference, P minus P3. So what is v? V is -6, 1, 2. And then I'm just going to project this onto N3. So let's call this projection, I don't know, W, let's say. So what's W going to be? W is going to be, well, the formula is something like, what was it? It was V dot N3 over N3 dot N3 times n3. At least that's the formula I remember, so I'm just going to go with that. Okay, so what do? We do, it's probably a simpler formula to use, by the way, but I can't be stuffed recalling the simpler formula, so I'm just going to use what I have in my memory right now. N3, and then another N3, and it gives me whatever this vector is, and then the distance, let's call it D, is just going to be the length of this vector, which works out to me, if I compute the norm now, it's just going to be 3 root 91 on 91. Yeah, 3 root 91 on 91. Okay, consider family of planes psi. That's the first time I've seen another Greek letter than, yeah, or at least this Greek letter in a VC exam. With equation, I can't even read the equation now. It's 6x plus 27z plus m. Show that the plane pi1 is parallel to each member of psi. So let's call the normal vector of such planes, let's call it n psi perhaps. So n psi is going to be equal to 6, 0, 27. And what is our n1? n1 is equal to, maybe I should define this as n1, and that was equal to 209. 209. So 2, 0, and 9. And as we can see, 3 and 1 equals n psi. So n1 is parallel to n psi. And because of that, yeah, psi is, I don't know if you can use the same, yeah, maybe. Psi is parallel to pi1. Let's say, therefore, finds all values of m for which the shortest distance between the plane pi1 and the plane of the form, well, this is psi, is 23 over 3 root 85. Okay, so what we can do, again, there's probably a formula you can use for distance between two planes. I don't have the formula in front of me right now, so I'm just going to derive everything from scratch. So let's take our plane pi1, and let's take our plane psi. And what I'm going to do is I'm going to, well, we know the normal vector. Let's just take the normal vector of these two to be 209. So we have n is 209. And what we're going to do is we're just going to choose 2 points on our two planes. And, well, this is going to be some vector. Let's call it v once again. And then we're just going to project v onto n. Okay, so I'm going to call this points that's living on pi1 p1, let's say. And I'm going to call the points living on psi, let's call it q. Okay, so what's the points living on pi1? Well, I look at pi1, y is free to vary. So let's choose, I don't know, z equals 0. So if you choose z equals 0, then x equals 4. So we have 4, 0, 0, let's say, because y is free to vary. So let's choose p1 is 4, 0, 0. And let's choose q. What's a point that lies on this plane psi here? Well, again, if I just choose z to be 0, y is free to vary, so we can just choose 0. So that means x must be m over 6. So m over 6. So let's plug that into the cas. I'm going to define p1 to be equal to 4, 0, 0. And I'm going to define q to be equal to m over 6, comma 0, 0. What am I doing? Define. Okay, so now let's compute v. So now I'm going to define v once again. I'm going to override that definition. V equals p1 minus q. So what is v? V is just this vector. V is 4 minus m over 6, comma 0, comma 0. Okay, now I'm going to project this onto N1, and I'm going to call this projection, once again, W. So whatever this projection is, let's use a different color. So let's call this projection W. So the distance, let's call it D once again, is going to be the norm of W, which is, well, I take the norm of, I project a V onto the normal, and then I do N dot N times N. So let's do that. So we have, once again, the dot product of V onto N1, dot product of N1 times N1, and I'm going to take the norm of this whole entire thing, and we get, that seems like it's going to be m minus 24 root 85 over 255. So we have a square root of 85, things are looking good. So let us now solve when this distance is equal to 23 over 3 root 85 with respect to m. And we've got m equals 1 of 47. So set d equals 23 over 3 root 85. And this gives us m equals 1 or m equals 47. Again, there was probably a much simpler way to do this just by using a formula, but I don't have the formula and I can't be stuffed searching it up. All right, hopefully I did everything right there. Question 6, final question. We have a stats question, classic stats, or a hypothesis question. So question 6. We have a volume of water consumed by students is assumed to be normally distributed. So we have n 1000 standard deviation of 80. And write down the mean and standard deviation of the sampling distribution. So mean is just going to be 1000. And sigma is going to be 80 divided by the square roots of 25, which is 80 divided by 5, which is 16. Okay, what is the probability that we consume, or the average consumed is greater than 970? Well, let us go to probability. We'll go to distributions. We'll go to normal CDF. Lower bound is 970. Upper bound is infinity. Mean is 1000. Standard deviation is 16. On the card should be inft ty. Maybe I just spelled infinity wrong. Infinity, there we go. 0.9696. Correct to 4 decimal places. So 0.9696. The canteen at a particular school stocks 2 brands of water. The manufacturer of Wassa dispensed. So standard deviation is 5. Sample size is 30. And sample mean is 750. Find the 95% confidence interval. So I'm going to do menu, stats, stat calculations. Sorry, not that. Confidence intervals, Z interval. And I'm going to switch to stats. And I'm going to go sigma is, what was it? 5. X bar is going to be 750. N, that's going to be 30, and 0.95. Okay, so we have 748.2, and then 751.8. Okay. The engineers decide to take 300 random samples. Okay, so we have each of these confidence intervals. They're 95% confidence intervals. So there's a 95% chance that it's going to contain the true mean. So if we take 300 such samples, the expected value This is just binomial probability now. It's just n times p, where n is 300 and p is 0.95. So if we do that, what's 300 times 0.95? It's 285. What is the minimum size of sample required to ensure that the difference between the sample mean and the mean volume dispensed is no more than 1 millimeter or 1 milliliter? So what we can do is, well, this is just margin of error. So we want the margin of error. What's the formula for that? It's the z-score times, it was sigma divided by square root of n. We want this to be equal to, well, let's just set this to be equal to 1 at the moment. So this is 1, but this is equal to, for 0.95, I'm pretty sure it was 1.96, times sigma, which was not 30, it was, is it 5? It is 5. 5 over the square root of n. So this implies that n is equal to, let's solve this in the cuz. So solve, we have 1 equals 1.96 times 5 divided by the square root of n, comma n. So we have 96.04. Now should we round up or down? Well, if we round down, we're reducing the sample size, so we're increasing the error. So that's no good, because we want it to be no more than 1 millimeter, so we better round up. So it's n equals 97. Okay, volume of water in these upper bottles are normally distributed with a mean of 750, standard deviation of 5. We have sample size of 50, and we find the sample mean to be 748. And now the company claims that the mean volume of water is less than 750. And we're going to do a 1% hypothesis test. Write down the null and alternative hypothesis. So H is 0. That's just going to be, well, the mean is unchanged to 750. H1, the mean is less than 750. Determine P. So the p-value, what we're going to do, so our distribution looks like this at the moment. So here's 750, and we have our 748, that was our sample mean. The p-value is just going to be this extreme probability here. So we're going to do probability, distributions, normal CDF, lower bounds negative infinity to 748. The mean is 750, and the standard deviation is 5 divided by the square root of 30. Was it 30? No, it was 50. And we got 0.0023. How many decimal places? 4 decimal places. So yeah, 0.0023. Okay, is the company's claim correct? Well, we're doing a 1% significance level, so yes, it is correct. What did they want? They wanted, the company claimed that the mean volume is less than, so yes, since P is less than 0.01, yes. Okay, so at the 1% level of significance, for a sample size of 50 bottles, find the critical value of the sample mean. So what does this mean here? The critical value, well, let's draw our distribution again. So here's the curve, here's 750, and we want to find this unknown value, let's say XC, X critical, such that this area here is exactly 0.01. So if it's slightly more or slightly less, it's either reject or don't reject. So maybe I should say yes, the null rejected, or something like that. I should probably put more thought into it, but yeah, something like that. So what we want to do is find this XC. So this is just going to be inverse normal. So on the cuz, let's go to probability, distributions, inverse normal. And the area, we want this to be 0.01. The mean is 750. Standard deviation, that was 5 on square root of 50, right? It was 5 and 50. All right. And we got 748, 355. So we have 748.355. Okay, final question. Assume that after the service, the true mean was 747. The population standard deviation is still the same at the 1% level. For the sample size, what we want to find the probability that the company will conclude that the service has not reduced the mean volume of water. Okay, so if it hasn't reduced its mean volume of water, that means we're in this probability range here. Or not probability range, our x value is greater than xc right over here. So maybe I shouldn't shade this in, it's not very meaningful in this picture. So what's actually happening, this was 750. Let's draw another picture. So here's our distribution under H0. And then we have our distribution under, let's say another, because the true mean we've found out now is something more like 747, the curve would look something, would be shifted to the left, something like that. So this is maybe not H1, let's say, yeah, H prime or something, I don't know. It's not really H1. What we found is x critical. X critical was living right over here. So this was x critical value. And what we want is this probability right in here. So anything above x critical, we don't reject the null hypothesis, but because h prime, this is actually the true distribution now, we want to find this probability. Okay, so that shouldn't be too tricky to do. We're going to go to probability, we're going to go to distributions, normal PDF, not normal PDF, normal CDF. So probability, distributions, normal CDF. The lower bound is now that x critical value, which we found was 748.355. The upper bound is now infinity. Let's make sure we spell it correctly this time. The new mean is 747.5. Standard deviation is 5 divided by the square root of 50. I can't type. Square root of 50. There we go. Okay, and we've got 0.1133. That should be right there. So 1133. Okay, so that's the whole exam. It was I found it to be fairly straightforward and routine actually. So VCAA definitely gave everyone an easier time this year. Definitely unlike some of the other ones I've seen in previous years. I think my one 2020 was pretty rough, and probably some previous years as well. So they've definitely toned down the difficulty a fair bit. Like somehow I'm still being able to answer these questions after 5 years, which is not what I'm expecting. I should be pretty washed up at this point. But yeah, that should be everything. Hopefully I got most things correct. If I don't, if I go over it again in the edits, then yeah, I'll add some annotations here and there. I'll probably have to edit a bunch of things because maybe you've noticed, but there's been a bunch of cuts here and there because I've been taking breaks in between to eat food and do other stuff. But yeah, if you spot any mistakes, please let me know. And yeah, hopefully you guys found this helpful. And yeah, that's all for this video, and I'll see you guys in the next one. Bye bye.